All right, let's dive in. We are going on a journey today, not into outer space, but deep into inner space. We're talking about the hidden, perfectly ordered world inside all the materials that make up, well, everything. We're talking about crystals. So, have you ever really thought about this? I mean, what gives a diamond its legendary strength, making it one of the hardest things on Earth? And at the same time, what gives a snowflake its delicate, one-of-a-kind, six-sided symmetry? They couldn't seem more different, right? But the secret to both their properties? It's exactly the same. Yep, the answer is all about how their atoms are arranged. Deep down, on a level we can't see, there's this invisible architecture, a perfectly repeating pattern that dictates everything about a material. And today, we're going to peel back the curtain and take a look at this incredible hidden world. So here's our game plan. First, we'll get a handle on this idea of hidden order. Then we'll check out the actual blueprints atoms use. After that, we'll figure out how to find our way around inside a crystal. Then comes the cool part, how we use X-rays to actually see all of this. And finally, we'll learn how to decode the strange patterns they show us. Okay, first up, the crystal's hidden order. You know, when you think about atoms, you might picture them as a chaotic jumble, but in crystals, it's the total opposite. It's the ultimate example of natural precision and perfect repetition. The core idea here, the very foundation, is something called the crystal lattice. Now, before you even think about atoms, I want you to picture an invisible three-dimensional grid of points. It's like the steel frame of a skyscraper before any walls or windows go up. It's the scaffolding. This lattice sets the rules. It dictates the precise locations where atoms are allowed to exist.
So if the lattice is the scaffolding, what are the actual building blocks that we place on it to create the final structure?
Well, that block is called the unit cell. And honestly, the best way to think about it is like a single Lego brick. You take that one brick and you can repeat it over and over and over to build something huge, right? The unit cell is exactly that for a crystal. It's this tiny, fundamental package that contains all the information, which atoms go where, and by just repeating it in all directions, you build the entire crystal. It's nature's ultimate efficiency.
Now it turns out that nature has a few favorite blueprints. Let's look at three of the simplest cubic ones. You've got simple cubic, or SC, which is, well, it's as basic as it gets. Then there's body-centered cubic, BCC, which takes that simple cube and sticks one more atom right in the very center. And finally, face-centered cubic, FCC, which puts an atom on each of the cube's 6 faces. And notice how as you add atoms, the coordination number, that's just a fancy way of saying how many neighbors each atom touches, goes up.
Okay, so this leads to a really important question, especially for scientists and engineers. In any of these unit cells, how much of the volume is actually filled up by atoms, and how much of it is just empty space? Well, we have a name for that. It's called the atomic packing factor, or APF. It's basically a grade for packing efficiency. And check this out. This chart tells the whole story. The simple cubic structure is actually pretty terrible at packing. Almost half of it is just empty space. But as you move to BCC and then FCC, the efficiency skyrockets. That face-centered cubic structure at 74% is literally the most efficient way possible to pack spheres. It's no accident that lots of common metals like copper and aluminum use this structure. That dense packing is a big part of what makes them, well, them. All right, so we've built this beautiful, repeating city of atoms. It's perfectly ordered. But how do we talk about specific locations within this city? How do we describe a particular direction or a specific surface? We need some kind of address system. And that's exactly what Miller indices are. Think of them as a GPS for atoms. It's this brilliant little notation that gives us a unique 3-digit address for any possible flat plane you could slice through the crystal. And this is so important in the real world. You know how a diamond cutter can cleave a diamond perfectly? They're not just guessing. They're breaking it along a very specific atomic plane, a specific Miller index address where the bonds are weakest. Now, this might look a little mathy and intimidating, but I promise the process is just a simple 3-step recipe. First, you just see where your plane crosses the X, Y, and Z axes. Second, you take the reciprocal of those numbers. You just flip them. And third, you clean up any fractions to get a nice, clean set of integers. That's it. That's your HKL address. So we have the theory, we have the blueprints, we even have an address system, but this is all just on paper, right? How do we prove any of it is real? How do we actually see this invisible atomic architecture? Well, for that, you need a very special kind of light.
You definitely can't use a normal microscope. The wavelength of the light we see is just way too big. It's thousands of times larger than the space between atoms. It's like trying to figure out the shape of a tiny pebble by watching a giant ocean wave go over it. The wave doesn't even notice it's there. But X-rays, their wavelength is in the same ballpark as the distance between atoms. They are the absolute perfect tool for the job. So when we fire a beam of X-rays at a crystal, they bounce or scatter off those planes of atoms. But here's the catch. We only get a strong, measurable signal back under very specific conditions. And those exact conditions are described perfectly by this one elegant, incredibly powerful equation, Bragg's law. It's the rule book that connects the X-ray's wavelength, the angle we fire it at, and that crucial d, the distance between the atomic planes. This idea of a selective mirror is the key. At most angles, the reflected X-ray waves are all out of sync, and they just cancel each other out into nothing. We see darkness. But when the angle is just right, when Bragg's law is satisfied, all those tiny reflections from millions of atomic layers add up perfectly, creating a single bright spot on our detector. Every single one of those bright spots is a clue.
And that brings us to the final and maybe the most mind-bending piece of the puzzle. We've done the experiment. We have our detector, and it's covered in this pattern of bright spots. So what now? How do we translate this dot pattern back into the atomic blueprint we're searching for? This is the final leap we have to make, because the pattern we get doesn't look like a tiny photograph of the atoms. It's more abstract. It's a pattern of dots. There's a missing translation step, and to make that translation, we have to learn to think in a slightly different space. Here's the key. We have to understand that there are two related worlds here. There's real space, which is the physical crystal we're holding, where atoms live. But then there's reciprocal space, which is a kind of mathematical concept, where our diffraction pattern, our dots, actually live. Every single point in this reciprocal space directly corresponds to a whole set of planes back in real space.
This is where we get our decoder ring. It's called the reciprocal lattice. This is the answer key. It's a mathematical transformation of the real lattice, and it's the tool that lets us do the translation. Every single dot we see in our diffraction pattern is one point on this reciprocal lattice. And because we know each point maps back to a specific HKL plane, we can start to solve the puzzle.
And here it is, the grand reveal. By analyzing the geometry of the dot pattern, which is the reciprocal lattice, we can immediately figure out the geometry of the real lattice. It's like seeing the structure's fingerprint. And here's the truly wild part. A body-centered cubic crystal in real space produces a face-centered cubic pattern in reciprocal space. And a face-centered crystal gives a body-centered pattern. It's this bizarre but beautiful inverse relationship. By looking at the shadow, we know exactly what's casting it. We've solved the puzzle. So think about where we've been. We started with a simple question about diamonds and snowflakes, and we've ended up here with a method for decoding the fundamental architecture of matter itself. Which leaves us with a final, really exciting thought. If we understand these atomic blueprints so well, what's to stop us from designing new materials from scratch, from the atoms up? What kind of future could we build if we become the architects of matter itself?